The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to North Carolina Science Olympiad, NCSO, and Young Engineers of Today. So we're going to continue with Arduino. No surprise there. We've got this class and we got the next one on Thursday, and those are going to be the last of the official classes, just so you know. So I'm going to try and leave as much time as possible on Thursday for questions and stuff like that. I want to probably try and split it about 50-50, just so we can keep that kind of stuff open and you guys know exactly what you're going to expect and, well, at least have a better idea, and try and make it a little bit less intimidating walking into the actual Science Olympiad competition. Anyway, that means I'm going to try and finish as much with inputs as I can get through today, so that we have, we don't have to front load it with just a whole bunch of information on Thursday, which means that maybe things might go a little bit faster today, maybe not. Who knows? We'll see. Anyway, so today is going to be about inputs. So everything we've done in the past has been dealing with outputs. We made lights blink. That's all output. Um, Now it's time to spend some time getting familiarized with the other side of the coin, which is the inputs. You're not going to have very interesting outputs if you don't have inputs that can affect them. So let's get familiar with it. So the lesson overview is analog read, serial print, and digital read. We're going to do analog read, then we're going to touch on the serial monitor, which is a very, very useful tool for Arduinos. And then we're going to get ourselves familiarized with digital read. And the reason why serial monitor is very useful is because it allows you to see kind of what's going on inside of the brain of the Arduino. You can see how its thought process is affecting the code that you wrote for it, in essence. Now, as a real quick review, words, as a real quick review of Thursday's lesson, the difference between analog read and digital read is a pretty big one, and it's pretty important to know. How many of you, by a show of hands, how many of you have or are familiar with the dimmer switches that exist? Like a little, like a knob that you can turn in order to make lights dimmer for, the dining room or something like that. Okay, mostly everybody. For those that aren't, it works pretty much exactly like I described it. It's just usually like a knob or like a slidey kind of switch or something like that, and you can turn the lights on full blast, or you can make them pretty dim, or you can make them kind of dim, or you can make them off. You've got an amount of freedom when it comes to how much you want the lights, how bright you want the lights to be, I should say. Then you've also got your regular plain flavor light switches, like maybe what you got in the bathroom or something like that, where you flip the switch and the light is either on or it's off. And there's no in between. You either just getting blasted in the face with a whole bunch of light, or you're fumbling around in the darkness. That is the difference between analog and digital. Digital is either full on or full off. Anytime you hear about digital stuff for a computer or something like that, that's because a computer's whole wheelhouse, its whole currency is ones and zeros and no in betweens. It's all the combinations of ones and zeros that allow us to see all kinds of pretty colors and listen to me, sort of ramble at my monitor in real time and eavesdrop in on that conversation. But there's no different value. It's all just 1 or 0. And that's the essence of digital. There are only 2 possible values. Analog, on the other hand, there's a whole slew of them. Mathematically speaking, there's an infinite value because there's an infinite range of values between even just 0 and 1, because you can have 0, 0.1, 0.01, 0.001, 0.0001, 0.00001, and so on and so forth. You can start splitting it into smaller and smaller and smaller things. There's technically no limit to how small you can break a number up. So that's why we say that there's mathematically speaking, an infinite number of different values. Realistically, we're not really going to be able to tell the difference between 0.000000000000001 and 0.0000000000002. So it doesn't really matter to us as much. But that's the difference between the two. Digital read is either on or off. Analog read is on, off, and everything in between. So we're going to familiarize ourselves first with analog read. Yeah, I think analog read is a simpler circuit to build. Yeah, analog read is a simpler circuit to build, so we're going to start with that one. So analog read is going to involve photocells, which are also known as light-dependent resistors. Now, a photocell or a light-dependent resistor is a resistor, just like the ones that you're plugging into, your 8 LED circuit and your 1 LED circuit, except they come with a caveat. Their resistance can change. As the amount of light shown on the resistor increases, it becomes a worse resistor. It becomes not as good at resistance. It becomes a lower powered resistor, however you want to think of it. As the ambient area becomes darker, or the resistor becomes covered over, or whatever the case is, as long as it starts receiving less light, it becomes a stronger resistor. It starts resisting more. So an LDR, or a photocell, is a resistor that changes its resistance based on the amount of light, hence light-dependent resistor. So that seems like a pretty neat toy. Let's mess around with that. Go into hardware assembly. Hardware assembly song. Sorry, I don't know why. Let me pop into Tinkercad, and I'm going to go into my circuits, and I'm going to create another circuit. Cool. Now we've got our blank circuit all ready to go. I'm going to drag out a breadboard. I'm going to bring out an LED. I'm going to bring out my Arduino Uno. And I'm going to bring out my photoresistor, just like what we got here. So we got a couple of other resistors. All right, so I'm going to bring out a couple of regular resistors as well. So we've got one photoresistor, one LED for those of you at home, 6 wires for those of you using Tinkercad. It doesn't matter because you just make them as you go. And then one 330 ohm resistor and one 10,000 ohm resistor, or 10 kilo ohm, or 10K ohm, or whatever your preferred nomenclature is. Although 10 kilo ohm is probably the most standard one. And we're going to hook them all up in a way that's useful for us. All right, so that's the 10,000, that's the 330. Cool. All right, let's get started on our circuit. I'm going to rotate my breadboard and rotate my Arduino. I'm going to bring my components over to this side. I said components, not you, Arduino. And first things first, like what is good practice in general for our circuit, I am going to set up the common power and the common ground. So I'm going to take the 5 volts from the Arduino. I'm going to plug it into the plus rail on the breadboard. Then I'm going to take the ground rail, or excuse me, the ground plug on the Arduino. I'm going to plug it into the minus rail on the breadboard. And just for keeping track of things, I am going to appropriately color them. So I know that the red is supposed to be the power and the black is supposed to be the ground. Then I'm going to give my resistors their proper resistance. This one is going to be 10 kilo ohms. and then this one is going to be 330 ohms. So we're going to type the 330, and you want to make sure you change the K ohm to the just ohm over here on the side. And we should have one orange, black, and brown resistor and one brown, orange, orange resistor. I know I read that backwards. It should be orange, orange, brown, and brown, black, orange. My apologies. And then we got an LED with a color of your choosing. I'm gonna make it blue because blue is a neat color. And let's go ahead and hook up our circuit. So, looks here like we've got the plus side of the LED plugged into pin 9 on the Arduino. Now, if you remember, the plus side of the LED is the anode. So let's go ahead and let's actually flip it around this way. Oh, good Lord. Ah. Oh, whoops, it's the anode. I know how my circuits work. All right, so I've got pin 9 on my Arduino plugged into the anode on my LED, which is the longer leg. You want it to be plugged into the longer leg. Then I've got the minus, or the shorter leg, plugged into the ground rail. So I'm going to color it black so that you know exactly where it's supposed to be going. It's supposed to be going into the ground rail. So this is important to note. The LED, or excuse me, the Arduino is plugged directly into the LED, and then the LED is plugged directly into... Oh wait, no, it's not plugged directly into the ground. What am I doing? It's actually... We're going to delete you, and we're going to take our 330 ohm resistor, and we're going to hook that one up. Boop. So our Arduino is plugged into the LED, and then the LED is plugged into the 330 ohm resistor, which is plugged into the ground. We want to make sure that we have the resistor, because why? Because fire happens otherwise. So make sure you have the resistor plugged into the circuit, because I don't want fire to happen. Or at the very least, a resistor, or excuse me, an LED popping. So that does it for that part of this Arduino circuit. We've actually got a whole another circuit up here for the photoresistor, and that's also going to plug into the Arduino, but that's it for the LED part, interestingly enough. And the reason for that is because we're gonna tell the Arduino to send certain amounts of power out on pin 9. And that power is going to be determined by whatever we get on the LDR circuit. So let's go ahead and hook that dude up. Now keep in mind, because the LDR is a resistor, remember resistors don't care which way they're plugged in. They're happy-go-lucky, easygoing, whatever you want to call them, but they don't care. So let's go ahead and let's just plug this resistor in however we like as well, as long as it's on one leg of the LDR. So as you can see, we've got row 5 here, bus 5, has got the 10K ohm resistor as well as the LDR hooked up to it. Then we're going to do a funky thing. We're going to have power run from here to A0 on the Arduino. So there's a lot going on bus 5 here. Bus 5 has an LDR, has a 10K ohm resistor, and has the connection to A0 on the Arduino. Then we're going to have the other side of our 10K ohm resistor. It needs to complete the circuit, so it's going to plug into the ground. Go ahead and make that black so we know exactly where that's supposed to go. And then we need to have power running from the plus rail to the other side of the LDR. So we're going to do that, and we're going to color it red. So this is our second circuit here. So we got power coming from the plus rail. It's going to travel along the LDR, and that's got two places it can either go. It can either go along the 10K ohm resistor and then hop over onto the ground rail, or it can pass it entirely and take our lovely wire here to A0 on the Arduino and send in power on the Arduino. So let me zoom in a little bit so you can regard this circuit for a moment, and then just go ahead and raise your hand when it is done. Okie dokie. That's just about everybody. So let's go ahead. Let's move on from here. All right, so what comes next is the coding bit. Exciting, I know. So here's our completed circuit. Let's take a look at the programming side of things. Let me get this open and delete this whole business. Excuse me, kitty. I'm a bit busy. Oh, yes. Sorry, talking to my cat. Like any sane person does. All right, so you'll notice that we've got a pin mode like we've done in the previous two programs. However, there are a couple of pretty critical differences here. First off, let's just type it in. You probably noticed that it's an input. Not surprisingly, that's because we're going to be taking in information on A0. Secondly, there's an A. I thought it just took numbers. Not quite. Pin mode can also take letters because it has to, because we've got these pins right here labeled with A. So you want to make sure that you're as explicit as possible with those pins. So pin mode A0 inputs. And this is going to set, analog pin A0 to be an input pin. That is to say, it's going to wait for electricity to go into it as opposed to wait for our signal to send electricity out of it. Now the pin setup, then in void loop, we're going to set an integer to a value. Let's see here, int LDR is equal to analog read A0. I gotta stop doing that. Well, interesting. If you remember in the previous ones, we had digital writes. Now we're taking in information on an analog pin, so it's analog read. If we were taking in information on a digital pin, it'd be digital read. If we were sending information out on an analog pin, it'd be analog writes. In this case, we're using analog read. And it's on pin A0. So we're taking the result of analog read on pin A0 and we're putting it into a variable, an integer variable, in fact, called LDR. That's what this means. So we're creating an integer variable, calling it LDR, and we're setting it equal to the value of analog read. So whatever analog read returns, it will fill into LDR. So far, so good, right? That's it. We haven't told it to do anything with the LED, but this is, for all intents and purposes, a completed circuit. Let's throw it into the code editor. We'll turn off block mode. Yeah, get out of here. Paste, and upload and run. And cool, we did it. It's running. Woo! Nothing's happening. This is not even remotely exciting. All right, that's enough of that. Simulate, turn off, simulation off. So as you guys probably already guessed, we set it up, but we didn't actually do anything with it. So the Arduino is doing all kinds of stuff going on inside its head. In its head, it's recreating this LDR variable, filling it with the analog read value, and then destroying it, just smashing it with a giant sledgehammer as soon as it hits the end of void loop, only to recreate it all over again, Groundhog Day style, as soon as void loop starts over again. Which sounds exhausting, but we didn't get to see any of that. And that's because the Arduino is a secretive mistress. It doesn't really talk to us. Or we just never really asked it for its opinion on what was going on inside its head. So that's the thing, is that ties nicely into the next concept, which is the serial monitor. The serial monitor is a debugging tool first and foremost, but it's actually something that's really kind of useful in general anyway. Doesn't mean you won't necessarily be using it primarily for debugging, because it's just spot on awesome for that. But regardless, anyway, the serial monitor and the serial print functions allow the user to view the data the Arduino is processing. As it says in the second thing here, incredibly useful tool like brain surgery allows for the user to get a direct look inside the Arduino. It's kind of morbid, but okay. And it can be quite helpful in informal troubleshooting. Ugh. Cool. So how does it work? Well, it's pretty straightforward. It's serial.print, and then whatever you want to print, or serial.println, and then whatever you want to print. Now, there's a little bit of setup that goes on before it, which we'll get into in just a minute, but these are your two serial print functions. What's the difference between the two, you might be asking? Well, I'm glad you asked. Serial print will print out the given variable. Okay. Serial print ln. ln is short for line. Serial print line, then, is the way you'd pronounce that. And what serial print line does is it prints the variable and then it does a new line. So the difference between the two is saying this would be serial print line. Except it's a computer, so it would be typing it correct every single time. Whereas serial print is more and so on and so forth. This can be a lot more difficult to read than this one, but there are cases in which you'd want to use serial print as opposed to serial print line for certain. So the trick is knowing when to use which to use when, whatever. So let's go ahead and let's set up some serial print for our viewing pleasure on the Arduino. So you'll see there's this interesting, other than the aforementioned serial print line here, there's this interesting little bit here that's serial.begin. Let's go ahead and put that in as I'm explaining what exactly that is. Serial.begin is a magic little thing. Basically, we need to tell the computer to be listening for the Arduino. whatever it's doing. Um, so we want to make sure that we're always paying attention to what the Arduino has to say, but we want to let the computer know that it needs to be paying attention to what the Arduino has to say. So that's essentially what serial.begin does here. Is serial.begin allows the Arduino to go, hey, computer, I want to be doing this now. This command tells the Arduino to basically start talking to the computer. And we need the Arduino to start talking to the computer. Because imagine if, like, whenever you had a conversation with somebody, well, there's always an initialization to the conversation to know that you're being talked to, right? Either somebody's looking at you or they call your name. Um, Less often, there can be an implied sort of address to you, like if you're the only person in the room, or they bring up something that you guys were just talking about a moment before, you can assume that they were talking to you. But in a lot of cases, there's some sort of cue to let you know that somebody else is talking to you, or to let somebody else know that you're talking to them. And that's essentially what's going on here. Is we're telling the Arduino to let the computer know that, hey, I'm talking to it. This 9600 here is basically is what's called known as the baud. It's basically sort of the transfer rate between the Arduino and the computer. 9600 is a good standard one. We'll keep it there. But if we check out tools and serial monitor here, as you can see, there's a little 9600 baud drop down, and there's a bunch from 1200, 2400, 4800, 9600, 19,200, 38,400, 57, 600, 74,880, 115, 200, 234, 25, 250,000. So it needs to be one of these numbers. So we're going to pick 9600. But that's done as far as that's concerned. Now it knows that the computer is going to be talking to it. And then we're going to serial.println, print line, and we're just going to print LDR. And what that's going to do is it's going to print the contents of the LDR variable to the serial monitor. And we just added 2 lines to the code, but you're about to see that your whole life is going to get turned upside down. So I'm going to copy and paste this code into here. And I'm going to open up the serial monitor and the little simulator. And I'm going to upload and run. And sure enough, look at that. I'm getting a bunch of 54s over here on my serial monitor. But watch what happens when I simulate the amount of light changing on my LDR. Hey, now it's just shot up to 974, and I can go halfway, and now we're looking at 949. And then I can go like 3/4 of the way, and I'm looking at 897, and a little bit further, 825, and then beep, 54. So the granularity is a little weird. It's really kind of all or nothing with the LDR, but by and large, you might see some better sets and numbers. But by and large, you will see some difference based on the amount of sort of light that you allow the LDR to receive. So by moving your palm closer and further away and stuff like that. So maybe I oversold it, but I think it's pretty cool. I don't know. What about you guys? Now you can see in real time the value that's changing. Oh my goodness. Wow. Now it's just a single value. And we haven't done anything with it at all. So, okay, whatever. But we can do an analog. Oh yeah, that makes it so it's easier to read. But makes it so it's more easy to read. But we can mess around with the LED in just a second. So this is a case in which you might want to use the serial print instead of the serial print line. If you serial print and then in double quotes, if you put something in double quotes, it will put literally, hence it being called a literal, onto the screen. So if we put that in quotes, it will print capital L, a capital D, a capital R, a space, an equal sign, another space, and then directly after it, because we have the print line, it will print the contents of the LDR variable, and then it will do a new line. So you'll start seeing output that looks like, oops, and so on and so on. So it's a way to introduce a little nice bit of formatting to it. We didn't really do anything with the LED. We can set up the LED to light up, but tell you what, we're actually going to get the digital bit done first, and then we'll combine the two in order to get an LED that lights up in a specific amount. All right, so let's see here. Yeah, anytime serial print is used, there's an automatic delay in the code you cannot see. This is simply because it takes time out of the processing to print the data to the screen. Nothing amazingly crazy there. All right, so let's get the digital read set up real quick so that we can read the digital input. Beep-barp. So we've got a 10,000 ohm resistor, and we've got a button, a push button. So let's get rid of our code editor. We'll open up components. We'll add the push button. And we'll add another resistor. And we'll close the components. We'll change this resistor to 330 ohms, just like we did before. And what I'm going to do is I'm going to have this push button straddle the middle of our breadboard. So as you can see, we've got it on columns E and F. And I've got it oriented so it's, yeah. I got it oriented so that the legs are coming out of the sides as opposed to up and down. Which if you're using Tinkercad like I am, that's the only way you can get it to straddle the middle. But anyway, oh, yep, no, it's not 330 ohms, it's 10,000 ohms. It helps when you pay attention to the stuff that you're doing. 10,000 ohms. Boop. Perfect. So, as you can see, we've got the 10,000 ohm is going to be plugged into the ground. So it's going from bus 10, which is the top part of the button, into the ground. And then we're going to have power go into bus 12. So let's go ahead and plug that in right there, and we'll make it red. So as you can see, power going from the power rail to bus 12, and then electricity, or excuse me, 10,000 ohm resistor going from ground to bus 10. And then we're going to have a connection from bus 10 on the other side going to pin 8. So let's go ahead and get that all set up. And we'll make it a nice purple color. So this is an interesting little circuit here, and our digital read is done, believe it or not. But why? What's going on here? Well, I'll tell you. So we got power. We got power. It's traveling down the power circuit, right? It hits this wire and it goes, whoa, and jumps across, right? So the push button has an interesting little feature to it. Anytime the push button is up, let me draw a push button over here. You can think of the push button as having two sets of circuits, and then there's one in the middle. Anytime the push button is up, the left and right sides are connected to themselves. So the electricity can travel along this way if it wants to. It's more than welcome to do that. If there was any electricity coming from this direction, it'd be more than welcome to travel along that direction. However, whoops, I forgot this erase the whole thing. Whoop. Meow. Meow. Whenever you press the button down, the circuit is completed. So now the electricity has the ability to travel along here, and it can go up here, it can go down here, or it can go back if it like. It can go any one of those three directions. And what we did is we put a very strong resistor right here. And the whole idea of this strong resistor is anytime the button is pressed and this circuit is completed, this right here will be the path of least resistance. And so it'll travel along into the Arduino and give us a result on pin 8. It will not want to travel this way if the button is pressed. And it can't travel this way because that's not a complete circuit. I don't know, sorry, 404, can't go that way. So that's the whole idea behind the push button, is anytime the button is pressed, the connection in the middle is completed, and then the circuit can travel, or excuse me, the electricity can travel along any of those paths, as opposed to just along the other leg. Cool. All right, let's check out the digital input. Okay, some information about pull-up resistors. Good to know. All right, let's add our button value. So we've got pin mode, 8 inputs, just like we did with A0 up here. We're going to make it an input. And then we're going to say int button equals digital read 8. Excuse me, 8. Boop. And then with the serial print line, instead of printing LDR, we can print button. Oops. And let's see what exactly happens here when we put this into the code editor. Paste. Serial monitor is running right here. Upload and run. Now we're getting a bunch of zeros. Click the button. As you can see, you have to hold down the button in order to keep the circuit complete. But when you do, you get ones. Nothing but ones. And then let go, and you're back to zeros. You can sort of create nice little patterns by pressing the button in a rhythm. Anyway, regardless, that's digital input. It's either just 1 or 0. You already knew this, though. Whereas analog input is going to be a whole range of values between 0 and its maximum. Now let's combine the two together. We're going to do something a little wonky here for the last 20-ish minutes of class. We're going to use the LDR and the button to make the LED light up. And what's going to happen here is the LED will not light up until the button is held down. However, the LED will be only as bright as there is ambient light with the LDR, I believe. Yeah, so as we light up the surrounding area more, the LED is going to be brighter. And as we cover over the LDR more, the LED will be dimmer until eventually it will no longer be on. So I should rephrase that. There are 2 conditions to cause the LED to light up. The button must be held down, and there must be at least a little ambient light for the LDR. So if we change this back to LDR real quick, upload and run, as you can see, at least on mine, I can very easily tell you what's going to be maximum and minimum value. Minimum value, full darkness, is going to be 54 on my LDR readout. And if I crank this all the way up to full sun, I get 974 as my maximum value. So 54 to 974. This is important to note, so I'm gonna mark this down for later. 54 to 974, and then I'm gonna throw in a couple of slashes so that it's a comment and the computer doesn't read it. So what could I be doing with that information, you might ask? Oh, that's an excellent question. I'm about to introduce you to a neato little feature that is called map. And I'm also going to introduce you to a neato little feature that is called an if statement. An if statement is pretty straightforward. All an if statement does is it says you've got the if, then you got some stuff in parentheses, and then you got opening and closing curly brackets. And all this does is it says, hey, if this stuff in here is true, then run this code in here. Otherwise, run this code down here. Now, here's the thing. I said that a little incorrectly. If this is true, run this code in here. Otherwise, do not run this code in here. See, this code is outside of the if statement brackets. So it's only inside of the void loop brackets. So it's always going to be run. So either this if statement is going to be run or it is not going to be run. But in both situations, whether it is or is not run, this code afterwards will run because it's just after it. So this might run and then it'll run it. This might not run and then it'll still run it. But here's the crux of the if statement. If whatever's in here is true, then run the code in here. So what could be true in here? Let's see here. If button is equal to 1. Remember how in the serial print we got the output of the button and it was either a 0 or a 1? And it's only a 1 if the button is held down. So if we hold the button down, we get 1s. I'm pointing with my finger because I have to hold down the mouse on that, which is really unfortunate because you can't see my finger. Sometimes I wonder if I truly do know how computers work. But anyway, so as you can see, there's a bunch of 1s here, and I let go of it and it becomes 0s. So we want to make sure that the button has to be held down in order for the LED to light up. So if button is equal to 1, that means that we're checking to see if is the button 1. If the button's 1, then that means the button's held down. So if the button is 1, then we're going to run the code here. Now, some of the more perceptive among you may have noticed that I've got a double equal sign here. And that just has to do with the nature of equal signs and the fact that computers, well, are dumb. So when you're doing mathematics, you might say, is 6 equal to 5? But you might also say, y is equal to 5. Well, let's say this. Is y equal to 5 or y is equal to 5? These are two very different statements. In one of them, you're asking if y is equal to 5, and the other one, you're saying y is equal to 5. They're two very different things. And we know which one it is based on context. Somebody says, hey, so answer this question for me, or it's written out like that, or whatever. Computers, on the other hand, take things on a symbol-by-symbol basis. They can't really read a context on a grander scale like we can. So the equal sign is reserved for assigning things. However, if the equal sign is reserved for assigning things, we need to have some way of telling the computer, hey, we're asking, is something equal to something else? In which case, we just threw another equal sign in there. That's not 100% the story. There are other things that you can do with it as well. You can also do less than or greater than. You can do not equals to, stuff like that. But the double equals is asking, hey, is this actually equal to this? If it is, then run the code in here. If not, then skip it and move on. So we've got our if statement here. If this value is true, so if button is equal to 1. So if button is equal to 0, the statement will be false because button is not equal to 1, right? If button is equal to 1, then the statement will be true, in which case it will run. So we'll say, is button equal to 1? If it is so, Then we're going to map a value. And actually, let me look up Arduino mapping real quick. Okay. So we're going to say a map. And what a map does is it takes two sets of values and it sort of creates a nice graph of the translation between those two values. That's really confusing. Let's put it like this. Let's say, for instance, because on an analog write for Arduinos, you can only send values from 0 to 255. You can send 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth, all the way up to 255, but you can't go any lower than 0 and you can't go any higher than 255. The wonky bit comes in because our analog read here is giving us values from 54 to 974, which is not ideal. So we start much higher than 0, and we end way higher than 255. So what we need to do is we need to say, hey, okay, so like, let's pretend that 54 we put into some imaginary math equation, and it came out to be 0. So 54 is our lowest value. We want that to be equal to 0. Then we stuck 974 into that same math equation and got 255 as a result. What we'd like it to do is we'd like to create a smooth set of results so that we could plug any number in between 54 and 974 into our equation and get a value between 0 and 255 as a result. So, for instance, we could plug in, oh, I don't know, 485. And because 485 is about halfway between 54 and 974, we'd get a value as a result about halfway between 0 and 255. It wouldn't quite be 127, but it'd be decently close. Or 128, excuse me. It'd be decently close. No, 127 is right. Anyway. And this could be translated. So like if we got a value that was about 75% of the way between 54 and 974, we'd get a value that's about 75% of the way between 0 and 255. So this allows us to translate it into a useful value for our analog write. And the way this works is we give it from low, from high, too low, too high. Okay, so we give it the minimum and maximum values of what we're working with, and the minimum and maximum values of what we want it to become. So 54 and 974 are my minimum and maximum values from the LDR, and then 0 and 255 are my minimum and maximum values that I can send out to the LED on an analog write. I know it's a bit of a confusing concept, but we'll expand more upon that on Thursday as best we can. Or we'll maybe cover other stuff, and then we can talk more about that if the questions happen to hit it on Thursday. And then we're going to analog write out on pin 9, and we're going to say value int value is equal to this map. So whatever map gives us as a result, we're going to feed into value. So on analog write, we're going to send value out on pin 9. And you might be saying, wait, this doesn't look like an analog pin. It's a digital pin. What are you doing, you madman? And I'm glad you pointed that out. But here's the deal. This little tilde here. Notice that this is analog in. There's no analog out. There's only digital. the little tilde means pulse width modulation, which is basically a fancy term for that describes a way that digital pins can send an analog signal out. It's like, imagine that you had that dimmer switch and then you had the little flippy clicky switch, and you simulated a dimmer switch with the flippy clicky switch by flipping the lights on and off really fast, just like absurdly fast. And you flipped them on and off so fast that the lights looked dimmer. And then maybe you flipped them on and off a little bit slower, and the lights looked more dim. And then you flipped them on and off faster, and then the lights looked brighter. And then you flipped them on and off so fast that like the lights just look on. That's basically what pulse width modulation is it's turning the digital signal on and off so fast that it looks like we're sending an analog signal. It's kind of an absurd concept, but you know, we're doing kind of absurd things. So we're analog writing out on 9 with the value from value. Now the final thing is we need to make pin mode 9 be output. And if we copy paste this whole business into our Arduino code editor, paste, upload and run. Oh, what's the last thing? Oh, value the number to map. Okay, so it's going to be, excuse me, it's going to be LDR. Silly me, I need to make sure that I put LDR in there because we need to tell it which variable to map. Paste, upload and run. Successfully compiled. Notice how our LED is off. If I press the button, the LED is still off. If I give it more juice, the LED is on when I hold down the button. I can give it less juice, and the LED doesn't quite look as on, but part of it is I can fiddle with the mapping features. So if I change 54 to maybe 454 and upload and run, we might see a much more sane gradient on our LED. Turn it up a little bit more, and we get kind of like a gradual lightening of the LED as we give it more juice until eventually we're at full power. And that was a couple of new features. I know we went over them really fast, but that's okay. We can expand upon them on Thursday. I'll try and spend a little bit of time on Thursday going over the next lesson, and then I'll try and leave half an hour for just like general question and answer time. And if you guys have questions about this, you can ask it then on Thursday, because we can go into all sorts of just sort of discussion about it and everything like that. But as it stands right now, I'm going to do the poll questions. If you have any questions about anything, I'm here. Otherwise, after the poll questions. Otherwise, after the poll questions are done, you're more than welcome to head out. Have a wonderful couple of days, and I will see you on Thursday.